Hello, this is Dr. Viv. In this problem, let us discuss the nature of the motion of a car on a banked curve. Now normally, if the road is flat and you have a car that's turning in a radius of r, there's some tendency of the car to be skidding in this direction. Especially in mountainous roads, you don't want that happening, so what you do is you construct banked curves. You can also find this in racetracks where the cars go really fast, and also in railroads and mountainous areas. The fast rails of Europe, you always find that one track is higher than the other when the train takes a fast curve, so that it's able to negotiate those curves without reducing its speed too much. What we are interested in finding in this problem is, in an icy mountainous road, find the maximum and minimum speed of the car. It might interest you to know that you can't move too slow or too fast in this situation. The coefficient of friction is given to be 0.1, which is typical of black ice. The radius of the curve, which is to say how big the circle is 100 meters in this particular problem. To start this problem off, we need to, as always, draw the free body diagram. The free body diagram in this case will actually not be a diagram with tilted axes, contrary to what you may expect. It's actually going to have straight axes. I'll explain the reason for this. My convention is always to take one of the axes to point in the direction of the acceleration. And in this problem, the centripetal acceleration a sub c is pointing towards the center. For the maximum speed case, let's call the centripetal acceleration a sub c 1. And I'm going to draw the minimum speed case right next to it for comparison. I will call the minimum speed case by the subscript 2. In circular motion, the acceleration is always towards the center of the circle. So it's going to be towards this imaginary pole in the middle. What are the forces acting? There's going to be a normal force perpendicular to the car, to the road rather, and acting on the tires of the car. Let's call the average normal force of all the 4 tires simply F sub n 1. That angle is theta. Now when the car is going at the maximum speed, it's going to tend to skid in that direction. So the friction force is going to be in the downward direction. That angle is also theta. So I have F sub f s 1. That's the friction force when it's just about to skid. Then there's of course the force of gravity acting down, mg, of the car plus passengers. Now in this free body diagram, the normal force direction is the same, its magnitude may be different, so I'll call this Fn2. Gravity is always going to be downward. The magnitude does not change. But now, because you're going at a slow speed, your car will tend to slide down. If it slides down, friction must act opposite the direction in which it would tend to slide, and so friction is going to, it's not sliding, it's going to slide. So it's an impending motion that counts. So that's FFS2. This angle is theta, and that angle is theta. So it looks like we have our free body diagrams all situated. In these diagrams, I also like to draw the direction of velocity. Now because the velocity vector is coming out of the page, the car is going like this, it's coming toward you, you're going to indicate the velocity as the tip of an arrow. We will use this notation later in the course when vectors are truly three-dimensional, especially in rotation and torques and so forth. So those are the free body diagram. The next step, as you may expect, is drawing the force tables, or rather filling up the force tables. Let's fill up the force tables for the maximum case first. Gravity, the force of normal has got x component in the opposite direction as theta, so it's going to be sine theta, and y component is cosine theta. The force of friction static has got x component of cosine theta and y component negative sine theta. Let's repeat the process for the minimum case. Gravity is unchanged. Normal force is unchanged, except I'll write 2 instead of 1. And then the friction force does change directions. In other words, the components simply interchange signs. Those are the force tables then. For both cases, the sum of forces in the y direction has to be 0, for the simple reason the car does not fly. So let us write that equation down first. I'll do it for everything for Fn1, and then we'll just do the replacements for this case. So let's just do everything for Fn1. So I get Fn, the sum of all these three things equals 0. So Fn1 cosine theta, all the positive stuff must equal all the negative stuff. So that's mg plus ff s1 sine theta. Now, the force of friction static is normally written as less than or equal to mu static times the normal force. But here, we're considering the case of about to slip, the maximum case. So I'm going to get FFS1 is equal to mu s times Fn. Let me replace that there. So I'm going to get Fn1 cosine theta is equal to mg plus mu sub s Fn1 sine theta. Let's save this equation as equation 1. In the x direction, all I would have to do is sum all the forces in the x direction and set it equal to mass times the centripetal acceleration, because it's moving in a circle. In the x direction, I only have those two forces. So I'm going to get Fn1 sine theta plus the maximum static force times cosine theta. Well, the maximum static force is just that, so I'll write it as mu s Fn1 cosine theta is equal to mass times the centripetal acceleration AC1. Okay, I'm now going to write the equation 1 directly below equation 2. This is equation 2. And divide. This procedure of dividing is an extremely useful procedure. I'll take this to the left side. Equation 1 I'll write in the following way. Fn1 cosine theta minus mu sub s. So this is 1 rewritten is what's happening in the denominator here. F sub n sine theta is equal to, and this common equal to sign, m times g. And now what we're going to do is realize that mass cancels. So this is valid for any car, which is an excellent good thing. It means that your answer will not depend on what kind of car you're driving. And that's a good statement to have for general motion. The other thing you notice is Fn1 also cancels. So I'm immediately going to get the condition. So I'll just copy down the condition from here. Therefore, the maximum acceleration AC1 divided by g is equal to sine theta minus mu cosine theta divided by cosine theta minus mu sine theta. Now, the acceleration is also equal to the velocity divided by the radius. So this is going to give me v1 squared over rg. That's what AC1 over g is. So I can immediately solve for v1. v1, which is the maximum velocity vmax, is simply going to be the square root of rg times, I'm also going to divide by cosine theta. So I'm going to get tan theta plus mu s divided by 1 minus mu s tan theta. Beautiful looking expression for the maximum speed. What about the minimum speed? You will observe that the only change for the minimum speed is the direction of friction, and that is tantamount to changing the sign of the friction coefficient. If you change the sign of the friction coefficient, that force will flip. So I can simply write down the expression for V minimum without doing any extra work. It's just the square root of Rg tan theta minus mu sub s divided by 1 plus mu sub s tan theta. You can see that decreasing the denominator and increasing the numerator indeed produces a smaller speed. Next, our numbers have to be put in. Now, fortunately for me, I don't have to waste too much time doing this because I, before making this video, took the liberty of running these numbers in my calculator. So I can write down the Vmax for the, I'll just show the number stuffing here, 100 meters times g, which I'll take to be 10 meters per second squared, tan of 30 degrees plus 0.1 divided by 1 minus 0.1 tan of 30 degrees. When I work this out, I get 34.17 meters per second, which works out to be something like 62 miles per hour. So that's the absolute fastest you can go on a curve like this. You can already see that banking enables you to go faster than you normally would in a curve. In a flat curve, you would not dare take a flat curve at 60 miles an hour unless it's banked. Highway curves are usually banked, like the one on 531. So there, people do go really fast between, I think, between Spencerport and Brockport or something like that. So let's look at the minimum. That's going to be 100 meters times 10 meters per second squared. And the only difference now is tan 30 degrees minus 0.1 divided by 1 plus 0.1 times tangent of 30 degrees. And that answer turns out to be 21.25 meters per second according to my calculator. And then That's approximately 38 miles per hour. I think the surprising thing in this problem is you can't go slower than 38. If you go slower than 38, then your car will tend to slide down the hill. That's actually a more dangerous situation because there could be some nasty stuff down here, like a swamp or a cliff. If it goes faster than 62, it will just go on that side and perhaps hit the mountain or something.